Hello.
Hello, Andrei.
Yeah, I can hear you, so everything works fine.
You will talk in English, right?
I think so,
Because
yes.
otherwise I don't understand any Russians. I'm not sure what's the protocol for this seminar, but
Uh,
if you
so we will wait. I think we will either Kola or Sasha, and if they are
no,
here, they can.
I mean for language.
If everyone, including the speaker, can speak Russian, then sometimes we switch to Russian.
Yeah.
But in some cases, even if there are no English-speaking people in the audience, we assume that somebody could watch the recording, and then we try to do it in English. Sorry, I'm looking for a stylus for my tablet. Must be some way. Yeah, I found it. Just I want to make sure, is everything all right with the sound now?
Yes.
Just because I used another computer, and I want to avoid this using both microphones. Okay.
I don't see any shared document if you share something.
Not yet.
Not
Not
yet.
yet. Just in a second.
Yeah, no.
Okay, so just please let me know when I should begin.
No, maybe you can just start slowly. And
No,
we are expecting
so
someone.
I don't know. It's up to you.
No?
No, if it's time to start, let us start. Just I don't know what are the
We
rules.
can try.
Okay. Well, I think that the talk might be short, so I will spend most time on motivation and the proof of the most interesting part. It will be reduced immediately to some mathematical papers. And I'm not going to explain the proofs of these mathematical results. I will only explain how our question about Kolmogorov complexity and information theory can be reduced to these mathematical theorems. Let me know if in this audience I should explain or motivate the definition of Kolmogorov complexity, or it's okay.
No, probably not. It will be
Probably
a
not.
time to a form of waiting for someone. But if we don't have,
Okay. I mean the plain Kolmogorov complexity, but the meaningful statements are valid within algorithmic precision. So if you keep in mind the prefix free version of Kolmogorov complexity, it's all right. Maybe the only thing that is not completely standard is the idea of relativization. So when I say that I relativize Kolmogorov complexity with respect to an oracle A, I mean that the programs, the decompressor, they may access this oracle A. They may read for free any information from this oracle. If this oracle is a finite object, then there is nothing new. This is just another way to define the conditional complexity. So we need a program that produces X using A as an input. But in general, it could be an infinite object and an infinite oracle.
yeah, I'm sorry. Probably I already asked this, and maybe you even answered, but I forgot. So imagine we have a kind of oracle, infinite oracle A. We are interested only in complexities of strings of length at most n. Is there some statement which says that we can replace A by some finite string of polynomial size, which is equivalent, more or less equivalent to the oracle for all x's of bounded length?
I doubt it. I don't. Okay. The answer is I don't know, but I would rather expect that the answer must be no.
So I guess it would be an interesting question, because sometimes we consider this kind of conditional complexity, and it's important to realize at what extent it can be replaced by finite things. Because if in your formula A is very long, even if finite, then if we start to use some inequalities, we get in trouble immediately.
But what would be wrong with the following argument regarding such a question? So
Yeah.
we run programs on all strings x of bounded length,
Yeah.
and then with this oracle A, and then we record all the questions the programs ask of A.
Yeah.
And
just
remember these questions and answers, and this is the finite object.
this is a finite object, but first we have 2 to the n program
Yes.
So if we want, if we this object is long, so the idea was that if we put this in the condition, then we want to deal with this A in the same way as we deal with other finite objects. So we consider everything up to logarithmic precision in the length of them. So A2. So we would not like to have A being longer than polynomial of n.
So you want the polynomial size
No,
of
the
n.
idea
Okay.
was that we can if we replace it, we replace it to be able to manipulate later, and to manipulate with logarithmic precision. It's very desirable that the logarithmic precision is the same logarithmic precision. If logarithm is complexity of x, this more or less makes
I understand. I understand the objection.
and also, if we should record the answers. Okay. Probably we don't need to record the questions. So the answers are just yes or no. So indeed, it's not very long thing.
But no, but the questions can be very, very long, right?
But
Because
the questions can be computed
the
from
program,
previous
right,
answers.
the
Why do we need
program
to
may
record them?
run in a time that is not that is not recursively bounded in n, and may ask a lot of questions from the oracle.
Yeah, but the questions, we can ask many.
Man, that's all right. We can enumerate the questions. It's not a problem.
Yeah, but there are too many questions. This is the problem.
I mean, it will. The answer could be not recursively bounded in n.
But even if we do not require polynomial length, the answer is unclear because there is another problem. Probably Sasha wanted to say also about that one. If we record all the answer, the resulting string has more information than those answers, because we write a string of certain length, and the length itself has more some information. And so it might happen that the complexity given that string is smaller than the initial relativized complexity for some strings.
Oh, yeah.
No, but I think that the most reasonable, the basic first questions which we would like to see the answer is whether we can have A of polynomial size. It would be a real. No, of course, we can also look at finite A, it's interesting also. But then we should explain how this A is produced, how it's given to the machine as a finite string or as a tape. What about the length and so on? But if it will be polynomial in X, it will be nice.
You know, I recommend to return to this question later, because we may this way postpone Andrei's talk too long.
Okay, but it's short.
Okay. This is a meaningless slide about the general motivation. So what do we want to know? What do we want to learn? We want to know which, given an n tuple of strings, we want to know which values of Kolmogorov complexities for all subtuples are allowed. So there are, in general, 2 to the n minus 1 values of Kolmogorov complexity for different subsets of strings. At least if we don't care about the order of strings in every such a tuple, then there are 2 to the n minus 1 values. And the question is which vectors of values can be represented as Kolmogorov complexities of some strings. Maybe not exactly, maybe up to a constant, maybe up to a logarithmic additive term. But anyway, which values correspond to Kolmogorov complexities? And a part of this question is the question about linear inequalities for Kolmogorov complexities. This question is it's in general, it remains widely open, but it is pretty extensively studied. We know that it is connected with a question about Shannon's entropy, with several combinatorial questions, with the question about the groups. But this is not what we are going to discuss today. Yeah, these questions get open. This is somewhat closer to what we're going to discuss today. It's not a question about this, so to say, conic span of complexity profiles, but about the structure of vectors inside of this conic span. So if we're given such a vector of complexities for some strings of some n tuple of strings, can we multiply it by some factor? For example, can we multiply it by 2? So can we find some other tuple of strings such that all values of Kolmogorov complexities are multiplied by 2? Maybe again within a logarithmic precision, up to adding or subtracting a logarithmic term. And maybe some people here know the answer to this question. Who knows the answer?
No, I guess it's yes.
I also think the answer is yes. Okay, but since Sasha believes that he knows the answer, we will not discuss this question. We will discuss the question where we want to transform a tuple of strings and another tuple of strings such that all complexities are divided by 2.
But about the previous question, still, it's I think important to say that there is no kind of direct argument. How do we construct this x primes from x? The idea is to use what Andrei started to do and always doing. We consider the set of all strings with the same complexities, which has some combinatorial proportions, and then we take a square, I guess, of this set, and it gets everything becomes bigger twice, and then we take a random point in this square. So it's not a natural argument, some kind. At least for people from Kolmogorov complexity side.
Okay, just I ignore your remark about this non-natural argument, but I agree with the plan. This is how we prove it here.
So this is indirect argument.
Indeed, a stage of this argument, of the only argument that I know, it uses the construction of the set of all, so to say, clones of the original vector of strings, the set of many, exponentially many strings, which behave somehow in a different way, which have similar complexity profiles. And then we deal with this set. We take a random element from this set, or two elements from this set to get twice bigger complexities, or 10 random elements to get 10 times bigger complexities. And this is the plan. Okay, but our question for today is not to increase the complexity, but to decrease it. In general, we could ask a question about multiplying by an arbitrary factor lambda, but let us ask the simplest possible question. Can we at least divide all complexity values by 2? Again, nothing magical in the factor 2, just the simplest version of the question that we can imagine this time. And as far as I know, this question is open if n is strictly greater than 3. Just we don't know how to answer this question. And perhaps trying to...
Sorry.
Yeah.
For 1.5, the answer is positive as well.
For 1.5.
Tau.
No,
And
No. I mean, you say open question for n bigger than 3. So
No. For,
n is not a factor, but number of strings.
yeah. Okay. Sorry.
Because for 3 strings, actually we know all the requirements which are we know the set, and it's indeed closed under multiplication by any constant.
Yeah, for n equals 3. Again, there is no a procedure to transform the original x in new x prime such that all values, all Kolmogorov complexity values are twice smaller on that. I don't know, 1.5 times bigger. But there is a general description of the set of realizable complexity profiles, and we know how to realize any vector in this set, at least within reasonable precision.
So as I understand correctly, we can show that for any integer lambda, this is true, and for any fractional lambda is unknown. Am I right?
For
Yep.
large n.
Yeah, for large n, yes.
Large n.
Yes.
Yeah. Also one can, if Peter allows one small remark, then that if we do this for variables, for random variables, for integer factor, we take independent copies. And for halved, there is a trick which we take our variables with some probability and trivial things with remaining probability, and it's almost half things. So it's somehow a replacement, but not... none of this trick has some clear counterpart in complexity.
Okay, and possibly with a plan to answer this question, or maybe with some other motivation in mind, Sasha asked the following different question. So let us assume that we are given some family, some vector of strings, and we know the Kolmogorov complexity. And can we find an oracle A such that when we relativize everything, all values of Kolmogorov complexity with respect to this oracle A, then all Kolmogorov complexities involving x's halves, or at least if we take, actually it's an equivalent question, if we take Kolmogorov complexity of every string, then relativization reduces complexity of each guy by a factor of 2. Yeah, by the factor of 2. This was the question.
And the positive answer implies the positive answer for previous question, because we can again use this typization argument. But it's
yes, indeed. If we could answer this question positively, this would imply the positive answer to the previous question.
I have a very naive question. So, what if we just take the programs, take the optimal programs for x's and their concatenations, and hide half of the programs in A? Half of each program in A.
Yeah.
And replace it by instruction, ask A what to do next.
It will work if all these x's are somehow independent, and the information contained in these programs is independent.
Okay.
In general, it could be that if we take some some partial information about the first program, we get already too much information about some others.
Okay.
Yeah, just I can say simple example. Imagine that x1, x2 are each part of it, and x1 is a prefix of x2, and they are the shortest programs for themselves. Then of course it's if we take half of the bigger problem, it will be either in the smaller part or not, and this is of course it matters. So it's not so simple.
Yes.
Okay, but anyways, we have a positive answer to this question, at least in the simplest case, when we have only one string. And in a few minutes, we will discuss it. We will see that indeed it's very simple. It is still just if we want to reduce complexities of individual strings, then it remains true for two strings. And I will also say a few words why this is true. And already for three strings, it is not true.
Even in the case if the third string is a concatenation of the first two.
Yeah, we will consider the case when x1 and x2 are two strings that are in some way correlated. We will need some special version of the correlation. And x3, indeed, it can be understood as the concatenation of x1 and x2. And already in this special case, we get the negative answer to the question.
Andrei,
Okay.
is this a new result for n equals 3?
Yeah, so it turns out just recently I've discovered that it follows from some theorem proven more than 10 years ago. I will show you a reference to this theorem. And we didn't know that so modulo this mathematical theorem, the proof is very simple. So we didn't know that the question is somehow resolved by Phil's laureates because we do not read their papers.
And there is another possible special case when x1, x2, and x3 are all prefixes of one another. Then we don't know anything, or there is also negative result.
I don't know. For this case, I don't know. Okay, let us answer at least the simplest version of the question. So we have a strings x. This is a string x. Of length n and bit string okay, n. And I want to construct an oracle which makes the complexity twice smaller. And okay, I'm pretty sure that you can do it in many different ways, but the simplest and the naivest way is to put into the oracle the first the prefix of x, a prefix of some length k. I don't know in advance which k we should take, but for some k it will work. Why it works for some k? Let us see how the relativized complexity of x changes when we increase k from 0 to n. If k is 0, the oracle is empty, then complexity of x given A is maximum. When k is equal to n, then the oracle contains the whole string x, and there is a very short trivial program which prints this x, just reads the bits of x from the oracle one by one. So here the complexity is almost zero. Here it is n, here it is almost zero. And when we increase
I'm
K,
sorry.
yep.
I'm sorry. What are questions to Oracle?
You can ask any bit from the Oracle. We don't care about time and space of computation.
I see. So
mhm.
actually, Oracle is truth table.
Yes. Yeah. Right.
Of some function. I see.
Yep. 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 Or
Yeah,
you
since here we deal with oracle of small length, we can also use a condition and use it as a condition string. It doesn't matter, but oracle is fine.
Yeah, here I could write complexity of x conditional on the string representing the oracle. It wouldn't change anything in this case. Yes. The dependency that I drew here, it is somehow continuous, or maybe purists would say Lipschitzian. Since when I add or subtract one bit at the end of the oracle, so I add one bit of information to this truth table representing A. This can change the condition complexity just a little bit. So the graph is a continuous function. It's somewhere it should cross the horizontal line, which is a half of n. And this is the whole argument. As I warned you, it's trivial.
Andrei, I'm sorry, not half of n, half of the initial complexity. You need to replace n by
instead of n, it should be c of x. But indeed, if we can first compress our x and replace x by its compressed version, which doesn't change complexity and oracle complexity. Then we can take just the first half.
Yeah, but I agree. It was a mistake. If I take if we do not compress x and just take the bits, the prefix of x literally, then I should write here complexity of x for this point and half of the complexity of x for this horizontal line. So somewhere here there will be the interesting value of k. Okay. Everyone is happy, right?
Mm-hmm.
Okay. Next question. Now the situation is I'm going to ask a very special version of the question. It's not just not just a pair of strings x and y. I fix in advance their complexities. Just you will see why it makes my life easier. But let us assume that complexity x of x and complexity of y are both 2n, and complexity of the pair is 3n.
So mutual information is n.
Yeah, so for those of you who likes drawing Venn diagrams, the complexity profile looks like that. Yes, indeed, they share the mutual information of n bits. And I want to find an oracle which reduces the complexities of both x and y by n.
But don't ask it to reduce any other complexities. Complexity of x, y can be arbitrary.
Yeah, complexity of the pair can be arbitrarily. We don't want to control it.
Yeah.
And the plan is to proceed as follows than the previous trivial case. I want to take m bits from x, the prefix of length n from x, and the prefix of length L from y, and join them in an oracle A.
No, the length should be also easier to understand. If remember, if there are big M and big L, because now it's kind of for picture it will be confusing. No, you have prefix M of another string of length M, which is a bit.
Length S. Is it better?
Okay.
Like that. Here is L.
Okay.
And T here.
Okay, to make everything. Yeah.
Okay. The only question how to choose those S and T. How to show that there exist values of S and T which make which do the job, which make both conditional complexities, complexity of x given A and complexity of y given A, y given A, how to make them both twice smaller than origin. And here we use the topological argument invented by Sasha Shen. We draw the space of possible choices for S and T as a square, as a two-dimensional region, as ranges between 0 and capital N, T ranges between 0 and capital M, and the choice of S and T is a point in this square. And for every point in this square, for every point here, we get the values of complexity of x given A and complexity of y given A. The first value ranges between 0 and 2n, and another also between 0 and 2n. It's also a value in the square. And what we want to show, what we want to prove, is that the point with coordinates n in both x's, it is covered, or at least a small neighborhood of this point is covered by this mapping, by this transformation. And before we discuss what happens with this transformation on all its two-dimensional domain, we will discuss what happens at least with simple points. So if I take this point 0, 0, it means that I put into the oracle the empty strings, and this means that the relativization is trivial. Complexities of x and y remain the same as they were in the beginning. So we get this point. So if this point is A, or A is, sorry, is used. Okay, O. So O is moved to this point. And let us look now at this point U. the point U means that S is and T are both maximum. I put into the oracle both completely X and Y, just a concatenation of both strings X and Y with all their bits. Then I can extract from this concatenation X or Y with only very small additional information. Basically, I need to know the length of X or the length of Y, some logarithmic information. So if we ignore the logarithmic terms, U will be mapped to this point. So it means that I get complexities for both X and Y negligibly small. Let us study now this point V. The point V means that I put into the oracle all X, but nothing from Y. Can you help me to find the point on the right corresponding to this V?
So
I put in
0 n.
complexity of Y. Then.
So complexity of X given A
0
becomes 0. So I must be somewhere on the vertical X, somewhere here. And what happens with complexity of Y?
It's conditional complexity.
N.
It is N. So yes, we're here, V.
V prime.
V prime, yes. And in a similar way, if I take a point W here, it will be mapped to W prime, W prime here. Great. Okay, we have found images for all interesting points. Now let us study the segment, the line between O and V. If I go gradually from O to V, then the image should go somehow from O prime to V prime, somewhere here.
In a monotone way.
In a monotone way. I don't know exactly how OV, which trajectory I will get here. I only can tell you in advance that all this blue line connecting O prime and V prime, it is above the horizontal line on the level N, because when I go along this line, everything that I put into the oracle, it is only part of X. So the conditional complexity of Y given a part of X, it is not, it is at least as big as the complexity of Y given the whole X. So it must be at least N. So it must be something like that. Actually, if you think of it for a minute or two, you will explain that this line should be somehow convex to the top, but it doesn't really matter. It matters that it is above the horizontal line N. And in a similar way, if I go along this line between O and W, the image will be some line between O prime and V prime, and its convexity is directed to the right. It must be all on the right with respect to the vertical line N, because the conditional complexity of X given this oracle, a part of Y, must be at least as big as complexity of X given the whole Y. Okay, and this is all this exercise. No, this is not the whole exercise of drawing. Sorry. Let us let us think what happens if we go from U to V. From U to V. If in this case, when we go from U to V, the whole X is already in the oracle, so we remain somewhere here. And we gradually reduce the complexity of Y. And in a similar way, if we go along this line, we go somewhere here. Okay, now the exercise of drawing is finished. Do you agree with the picture that I have drawn so far?
Yes.
Okay, and now the moment where Sasha Shen is saying, okay, let us use some kind of topology. Actually, I don't know what is the name of this theorem from topology. Maybe Slava knows.
Jordan.
The official.
Jordan?
No,
it's too
no. Maybe Brouwer's theorem or
No.
I want to say that if a square or if a circle is mapped to a circle, then the internal part of the disk. Sorry. Let me start again. We're mapping a disk to a disk. Topological disk to topological disk.
Well, let's just say one topological sentence. If we consider a homotopy of the path on the left to a point, then the image should go through the red point. Otherwise, we get a contradiction because it was not the index was 1 and now it's 0.
So it's called Jordan curve theorem.
Not really, it's much simpler.
It says that the complement of the image of a circle has more than one component.
This is a difficult theorem, which I don't know. But what we know, what we need is much simpler. No, for topologists, it's all the same. But for simple people, it's much simpler.
Okay.
I think it's still not trivial theorem, even though it's intuitively very simple.
No. Sometimes, at least in Russian books, it's called a theorem about a drum. That if you want to construct a drum, there is no a hole inside. If you know how, if you have a continuous mapping and you know what is happening on the borderline, then every internal area inside of this borderline should be covered by the image. It can be proven in many different ways, and one of the proof is what Sasha has suggested. We can gradually contract the borderline on the left to the central point, and on the right we will see some circles contracting to also to some point, to some.
Yeah, but the fact that you go through the middle of the right square is exactly this Jordan curve theorem.
Not really. No, it's enough to consider index. So if we go to the center of this to the red point, then the angle. The number of rotations around this point is well defined.
Yes, index theorem requires to prove that the circle is a cycle.
Sorry?
Okay, it doesn't matter. So we don't have to dwell on this.
Okay. We don't know how to call this theorem, Jordan or not, Brouwer or not. Anyway, everyone is sure that.
Wait. We are discussing some theory, continuous theorem. What do we require on the function?
Okay. So how we there are two continuous to discontinuous case.
Okay, there are two ways to answer your question. One way to answer your question. We reduce our discrete question to the continuous one. So, in fact, you're right. Formally speaking, we have a function defined not on real numbers, but on a discrete grid.
No, Andrei, my question was about the theorem about real valued function. What do we?
It must be continuous.
Continuous?
Yes.
It's enough to be continuous.
Yeah.
Yes, it's enough to be continuous.
And we do not require that it is sort of bijection, just continuous.
No, absolutely
the
not.
argument doesn't depend on this. If we have homotopy in the left-hand side, it just continuously changes in the right-hand side. Continuity is all we need.
And don't we need the continuous of the inverse mapping?
Not at all, because we consider only the images of this circular path. Initially, they go into the red point once, one rotation, and in the end, they make zero rotation. So if they never go to the red point, there is a kind of contradiction here. Ну, число оборотов вокруг красной точки должно меняться непрерывно при стягивании пути. А вначале оно равно единице, а потом нулю. Значит, если мы не проходим через красную точку, то получается противоречие.
This is homological argument, and it requires, I mean, the whole definition of homology requires Jordan curve theorem.
Not really. Накрытия совершенно достаточно. Okay, let's...
Okay, well, I hope I convinced you that we have an answer to this question to A. At least maybe we need. Maybe we need
how we reduce a discrete case to continuous case.
But people told me that I shouldn't care because it's obvious.
Ну что, можем продолжить. We can extend the function continuously. Okay.
Yeah, we can cut this grid on the left into squares or even into triangles, and extend it continuously inside of the triangles, and then we get
some point gets exactly to the red point, and the close point will go close to the red point because they are discretely continuous, so to say.
Well, essentially, you need to use the Lipschitz property of the original map.
Yeah.
Sure.
Yes, you're right. This is true. But perhaps somehow philosophically, it's not. It is strange to switch from a discrete question to continuous, and then apply some discrete machinery of algebraic topology if you want to prove this continuous statement using this homology of a circle. But probably it would be more honest to reduce the original question directly to Sperner's lemma or some discrete version of this statement. But let us skip this part. Just let us say that we believe that this statement can be proven using a kind of topological intuition. At least what is Sasha is saying to us for several years, and we believe.
No, actually, I don't remember. Maybe Bruno, maybe you were somehow involved in these discussions. Not so. I'm not sure.
Yes, but it was 10 years ago, so I forgot everything.
Okay.
I remembered about Sperner lemma, and I thought it followed from this, but it's too long ago to say something.
Okay.
But anyway, I told you that I'm going to explain how to answer the question only to the very special case, to very special values of x and y. Maybe you can guess what might be wrong with this argument for different x and y with different values of Kolmogorov complexity and mutual information.
So you need convexity, which you mentioned, yeah?
We need this point in the center to be below the line between O prime and V prime, and to the left from the line between O prime and W prime. And it is not always the case if the mutual information is very large.
But doesn't it, if it's convex, then it should be, no?
No. No, just what for the line between O prime and V prime, it could come somewhere here. So, and all the image could sit somewhere here. At least the continuous argument doesn't explain why this is impossible.
I don't get it. But just the middle point should be on the vertical axis, no?
So do you know the information about the V prime and W prime? Then monotonicity would suffice.
You know, V prime is on the vertical line, but it can be just go down.
It could be below. It could be below the level.
It could be below. But still, if we have convexity, then the red point is okay. Still, no.
I guess that the complexity of the pair is always at least 2n. And this implies that O prime is always above n.
No.
And the right of n.
O prime is above n. Yeah, but V prime can be close to 0 if they are large mutual information.
Can we write on what assumptions are we trying to look at it?
No, let's first discuss whether we can ignore.
No. Let us postpone this discussion. If we don't have time to come back to the discussion, it will be homework. Whether we need a convexity, whether we're allowed to use a convexity. Just right now, let us stop with my own personal claim that I cannot I cannot adapt this argument to arbitrary x and y. However, there exists a different alternative argument which explains how to construct such an oracle in the general case for arbitrary x and y. Just I will sketch very briefly how it works, and then later we can discuss how to prove the same thing using topology. Okay. So I'm trying to draw this Venn diagram for the complexity profile of x and y. M, L, S. Assume that M is greater than S. In fact, this oracle can be so in the topological argument we explain that the oracle exists, but we do not construct it explicitly. It can be done in more constructive way, in more explicit way. So Muchnik's theorem on conditional description, it claims that we can find P, string P, which is a part of Y. It's P such that P given Y is negligibly small, and a complexity of P given X. Okay. Sorry, just I fix the value of the length of P, And I say that complexity of P given X, it will be as large as possible. It will be either the length of P itself, or if P is too long, then it will be just S. So somehow it means that we can put in P the entire this part Y minus X, and maybe also a part of the intersection. It's a very metaphorical and imprecise statement, but this is the idea. We extract from Y a kind of hash value, a kind of fingerprint, which looks maximally random with respect to from the point of view of X. And we will choose T, the length of P, a half of complexity of Y, 1/2 of complexity of Y, which is 1/2. In my notation, it's L plus S. And the oracle, it will consist of the concatenation of, it will be the concatenation of P and plus some other string Q, and Q will be defined in a similar but symmetric way. Complexity of Q given X will be 0, and complexity of Q given Y will be maximal. It will be just complexity of Q. Q will be, it will live somewhere here. This will be Q. And I will choose the size, the complexity of Q such that okay, I will choose the complexity of Q such that complexity, conditional complexity of X given P and Q is the half of complexity of X. So instead of it is similar. It is in some way it is similar to the topological construction of Sasha, but instead of taking the prefix of X and the prefix on Y, Muchnik recommends to take, so to say, a random hash value. Formally speaking, we need to apply a randomness extractor and what is written here, and take the value of this extractor. So, and it remains only to choose the lengths of these hashes, the length of a hash of X and the length of the hash of Y. And if we choose them in a here and here in the right way, we get what we need. Okay, and if you want to do this exercise and to verify that if we choose the lengths of P and Q in this way, we get exactly what I promised, then okay, it could be also a homework number 2, or we can rediscuss it after the third part of the talk. Any question here? Okay, and now we're arriving finally to the interesting part of the talk when where I'm going to say something that we didn't know just a few months ago, because we don't read papers of serious mathematicians. Yeah. We're coming to the negatives result. I'm going to show that the answer to the general question of Sasha is negative, even in the case where, in a pretty special case, where x1, x2, and x3 are x, y, and the pair x, y. Length of x will be 2n, length of y will be 2n. Okay, concatenation will be of length 4n, but x and y, they will be correlated. The mutual information of x and y will be equal to n. And I'm going to construct x and y such that it is impossible to find an oracle which reduce complexities of everything, of x, of y, of xy, by the same factor of 2, which divides all complexities by 2. That's the plan. Okay, the answer is no. And moreover, I can tell you how I'm constructing those x and y. I will take a discrete plane, an affine, or if you prefer, or projective, and in this finite plane, I will take x as a line and y as a point in this line. And it will be a counterexample to Sasha's question, like a negative answer to Sasha's question. If x, this pair x and y is chosen, so to say, at random, with the maximum possible complexity, and this is crucial, the field, the plane must be constructed over a finite field. If it is a field of characteristic 2, for example, then the answer to the question is positive. We can divide complexities. We can divide all complexities by 2, but with a prime field, this is impossible.
So prime field is
what is the prime field?
P to the
Sorry?
n is also prime, or not?
No. The size of the field must be a prime number.
Okay.
The characteristic of the field and the size of the field are the same thing. Yeah. If it is a field of the size p, if p is a square of some other number, like a square of prime number, then the answer to the question would be yes. So the answer to the question is positive if we can find in the field a subfield of a quadratic size, quadratic square root, size of square root, and the answer is no if the size of the field is a prime number. Yeah, the field must be prime. Okay. Let me explain the combinatorial statement corresponding to this claim. Just assume, for the sake of the argument, that there exists an oracle A such that complexity of X, complexity of Y, and complexity of X and Y given A, they are equal to n 1.5 n. And then for this oracle A, I define the following graph. In this graph, on the left, it will be a bipartite graph, and the vertices on the left are points in the plane, points such that complexity of this point given A is at most n bits, like for our point X. And the vertices on the right are lines in the plane such that the complexity of this line given A is at most n, like for our line Y. And the edges in the graph are pairs of incident vertices, or pairs of incident lines and points. So I connect two vertices by an edge if the point in the left lies in the line on the right.
Independently of the complexity of the pair.
Independent of the complexity of this pair. Okay. What can we say then? Okay, first of all, if I'm given the oracle A, then I can run all programs of length n in parallel, and I will see how this program stop one by one, produce something, and I will gradually discover new vertices in this graph, new points and new lines with a suitable conditional complexity. And I will gradually, one by one, discover the edges connecting these vertices. And at some step, at some moment, I will in this enumeration, I will discover the pair x, y, the real x and the real y from our example. And what can we say? We can say that complexity of xy, the pair xy given the oracle, is at most the logarithm of the number of edges, in this bipartite graph, plus some negligible overhead required to organize all this enumeration. Yes, we need to know, basically we need to know the prime, the size of the field and the number of bits in this field, which is n. So why I am saying this? If we can somehow bound the number of edges in this graph, if we can prove that the number of edges is significantly smaller than what I promised, much smaller than n.5, then we get a contradiction. So the combinatorial statement that we need is as follows. I take a projective plane over a finite field. I take some set of points, some sets of points and some set of lines, and I count the number of incident pairs. And I need a non-trivial upper bound on the number of incident pairs. And this is a geometric or combinatorial question, and you don't need to know Kolmogorov complexity to explain it. So it's not surprising that people who don't care about information theory and about Kolmogorov complexity, they asked this question. And moreover, they found the answer to this question, at least some partial answer to this question. I will show you two versions of this answer. The historically first statement, somewhat weak. It is already enough to get a negative answer, the negative answer to Sasha's question, but it is relatively weak. And on the next page, I will show you the state of the art, what people can do now. So this is our theorem proven by Burgen, Katz, and Tao more than 20 years ago. And okay, just let us read what it is written here. They say if we take some set of points and some set of lines in a projective plane, and if the number of points and lines are both bounded by L, then the number of incident pairs is bounded not by L to the 1.5, not to the S times square root of L, the trivial bound, but what is written here.
I'm sorry for a stupid question, but if you take L equals what is the number of points p squared, yeah?
Yes. We get exactly p cube.
Yes, so you get exactly the exponent 1.5.
Yeah, indeed. L should be smaller than something.
Yep, yes. Yep. You're right. You're right. So here we should say that L is smaller. It is smaller than P is the size of the field. It is must be small. Okay, let me write something stupid. Something smaller than 2. I will write here 1.99. Yes, we need some upper bound on the size of L. In our case, L must be significantly smaller than maximal value. In our case, L is something like P. It's a square root of the total number of points and square root of the total number of lines in the plane. But you're right. If we want to a general statement, then we need some upper bound on L. Then we have this bound. Yeah, and this is how it works. In our application. We bound the complexity of x and y given the oracle is as the logarithm of the number of incident pairs, and it turns out to be smaller than what we want. smaller than 1.5n, or so it's on the exponential scale, it's logarithm of this thing, which is a logarithm of square root of the number of all incident pairs.
So if we had just 1.5 without epsilon, then it will be also not trivial, but it's just a corollary of the fact that there are no 2 points go on 2 lines. Two lines going to the same 2 points. And here it's just something stronger, and this is why we need special thing about prime numbers. And
in the paper of these people and other people working this area, the claim that you have done, it is called trivial for them. Indeed, it is simple. But you're right. This is the bound 1.5 could be proven actually for every field, regardless of its structure and its characteristic. So the bound with 1.5n, it is true for every field, and it can be achieved. This bound is tight if in the field is a subfield of the size square root of P. And the last page, the state of the art. At least Ilya Shkredov recommended me this paper, saying that this is the best what people can prove now. So in the original paper, there was some epsilon. It seems that people didn't even try to compute exactly what epsilon they are able to prove. Now we see quite a significant progress. So when the sizes of V and W are comparable, close to each other, then we have this bound ML to the power 11/15.
And again, they should not be too close to the size of the field, I guess. There should be, because when they go to the size of the field, we go to 3/2.
Yeah. And L should be smaller than the size of the field. Yeah, you're right.
No, I guess if you have 1.99, probably you cannot get 11/15. But this should be something more. But anyway, it's okay.
Okay, just it's easy to verify that I will open the paper and we will find the statement.
Okay, maybe while we can, or maybe it's not so important, just I have another question, natural, I think. So imagine we don't want to use the planes and lines and just want to construct some graph with this property. Is it the only way, or if it, for example, take a random graph or take a Hamming distance graph or whatever, there are also chances to get this?
For Hamming distance graph, I'm pretty sure that it will not work. For a random graph, most probably it will be fine. Yes, I didn't check this, but I believe it should be the case for a randomly chosen.
It's very strange for a random graph if you restrict to some subset, you again obtain a random graph. So the density should be comparable with the.
Yeah, so which means the density will be smaller.
Why?
No. If the density in the pair is the same as the entire graph, of course we get something less than three halves. 3/2 mean that we have just the density as in the field of this size, and in a bigger field the density is smaller. I think.
Yeah. Okay. It seems that I found. It seems that I was too optimistic. It seems that they say that L and M that they're smaller than the at most P, not 1.99, not almost P square, but rather just P. It's okay for our application. It's exactly what we want, but the bound is stronger than you could expect.
So what you say that if we don't care about nice geometric example, actually you think we don't need Phil's medalists to get this negative answer. It can be obtained by some random graph.
Okay, I have two answers to your question. First, okay, let us say it's a conjecture that these are probably stronger bound could be proven for a random graph. And second, so these people, I'm absolutely sure they're very smart, but even though they're maybe as smart as Phil's medalists, it seems that they simplify the technique significantly in 10 years. In the original paper by Bourgain, Katz and Tao, they used some subtle techniques from additive combinatorics. And again, I cannot explain you the proof of Stevens and Duserve, but it seems that what they use, what they write in the paper, and what is written in the paper that they employ and that they cite, it's an advanced version of polynomial methods. So if you remember the Dvir's proof of the bound for Kakeya set, it seems that what is happening here, it's something of the same style. So it's possible to understand, but don't ask me to explain the proof today.
But Sasha says that if you take a random construction, you give much simpler proof.
No, it's no. We need to do something. It's not obvious that random construction will work. They need to check things carefully. But indeed, maybe Misha is correct that still even with the simplification, the random construction could be simpler. Yeah.
Possibly, yeah, possibly.
I have another question. So in the reduction, it's enough to just find one set of P points and P lines with few edges, right? And so
it depends on, okay. If
so you want to prove the negative.
Yeah. Imagine you have one set of points and lines with few edges. So what?
So then you declare them to have small Kolmogorov complexity, and so a random point and a random line will have complexity close to log P.
No, I don't understand. So you start with X and Y being taken from where? From an entire random line and point, or not anymore?
So first from the field we get the graph, the bipartite graph.
Yeah.
Then we want a theorem that says there exists a set of points and exists a set of lines.
No. The theorem said that there exists an X and Y.
Yeah. And then we say that all the points in this set X in the set of points and set of lines, they have small complexity. They have complexity log p, all of them, at most.
Yeah.
And then if we know there are few edges, then we know every edge has small complexity. And so then we get the proof that we want. So if we then in this special set of points, we take a random point that will be our x. And then we need a neighbor of this.
No,
and we can no guarantee.
There is just basic problem. There is some claim for every oracle something happens. And before, depending on the oracle, we get some subset. And so we need something for every subset. How do you want to avoid this?
Sorry. Yeah.
Okay.
Sorry.
For every oracle. You cannot somehow ignore this completely. Now, if you want to construct some x and y with some properties, then you can use a small subset with some properties. But for two strings, we don't have anything interesting because we know which combination is possible. So no special combinatorial set will help.
Okay, sorry, I need to think again. I misunderstood something.
Yeah. And what do you think? What should we do if we take x and y with Hamming distance? We just probably we should just have the first half of the things, or what?
No, okay. I guess that's the answer to your question must be also negative if you take x and y from Hamming's graph, but the bound. No. Sorry. Yeah. Exactly as you suggest. Yes, we can take
Somehow
a half of
we
positions.
already have some independent copies.
Yes.
And we just half of that independent copies
Right.
probably will
Exactly. We take a half of positions and put in the oracle half of positions of x and y. Yes. Yeah, and the last thing I want to say, just a fun fact. So somehow this paper of Bourgain, Katz, and Tao in 2004 answered the question that we raised in our question in 2002. I know, of course, they didn't read our paper, but somehow by this lucky coincidence, we have these great people who answered our stupid open question.
But there is a general thing. So if general question which I think deserves to be somehow studied. So imagine we have some graph, like this or any other graph, and then we consider a random point xy, and we consider possible things if we add arbitrary third string, that's what is called extended profile. We take x, y, and arbitrary z and see what is possible. And it seems that it should be somehow related with the combinatorial properties of the graph. So here is just one specific relation. So if the graph has this property, then you cannot find z that halves all the complexities.
Yeah.
But it would be nice to have some more back and forth statement, which translates somehow one thing to another.
Okay. It would be nice, but I think I'm afraid that it's there could be back and there could be forth, but not equivalence. So first of all, I think you mean that a graph is somehow nice. I don't know, edge transitive.
Edge transitive is good idea,
yeah. Then we have quite a few partial statements of this type. For example, we can prove that if we have some bound for the second eigenvalue of this graph, then we can say something about this extension profile. But there is no equivalence statements, unfortunately.
No, imagine we don't, about the graph, we are allowed to make some complicated combinatorial statements. So for every pair of set A and B, there is the number of edges, I don't know, allowing quantifiers, but still requiring the statement to be combinatorial. Do you think that there is no way to translate the profile question in this way?
No, I cannot answer this question because I don't know in advance which statement is still combinatorial for you and which is
doesn't involve complexity, just very simple.
Andrei, did you look at the Kneser graph?
Yes. Yes.
So
just I'm not. This is indeed a natural example. Just sorry, just somehow I'm stuck. I'm not. I cannot tell you immediately what is known about Kneser graph in this context and what is not. But okay, maybe in a half hour this comes back to my mind, and then I will send you an email. But sorry, just somehow it's
no rush.
No. The problem with the Kneser graph is that it has a very small very small spectral gap, a very small gap between the first and the second eigenvalue, and this explains that in some sense it is this hard to handle. But I'm not ready to give a more reasonable answer.
And also, let me say why I'm asking about this combinatorial thing, because there is a question which I advertised several times. So there is a dimension result saying that on every line of some dimension, there are points of dimension from some interval in a real case. And there is also a finite case. Imagine we have a line of some complexity. What do we know? Can we, for example, claim that points on this line have have complexities in some interval? And what can we know about this interval, or just and this somehow, if it's translated to combinatorial question, maybe the Fields medalists also already have the answers.
No, I don't know. So,
okay, so let's now, if no more questions, let's thank our speaker. And what will be the next time?
So I still think we need to hear the second part of Ivan Baburin's talk about universality.
It will be a good idea, but it would be nice if someone also would look at the paper and will help him to explain this what he was done to stupid listener like me.
But
have you looked, by the way, Kolya, or not?
No, I haven't. And anyway, I asked him to deliver the second part of his talk, not the next week, because I thought that the next week we would have again Andrei. Okay, so
no, we are also always delighted to have Andrei. Can we have Andrei in next week too?
No, you cannot have me next week. Just all next week, I will be in a workshop.
So
But I don't
probably
promise to give.
next week we can skip the meeting, the next meeting, because on April 7 we will have another guy.
What will happen in
which
April
happens
7th?
to be Ivan Baburin's advisor.
And who is this guy?
Now let me check. Oh, wait a moment.
And also, while you're checking, Bruno, have you some text, a new version of the text ready?
Well, I wrote many proofs and then realized the first proof was the best. So yeah, and tomorrow I will send it.
Okay, no problem. Just
So his
I
name
was
is-
afraid that we didn't have it, but if we lost it. But no, if it's not.
No. Yeah, I tried many things to make the proof more natural, and now I think it's good.
So his name is Matthew Cook. Like
it's
Stephen
very
Cook,
important guy.
but not Stephen.
Who
Matthew.
in some way proved he was the first who proved that some Wolfram automaton is universal in some sense. So he should know very well in which sense it's universal and why.
Yeah, and after that, the next week, I mean, April 14th, we will have again Ivan Baburin. So we will understand him better after Matthew Cook's talk, I guess.
Okay. So if we have already specific plans, then we will skip next week's because of Andrei's workshop, and
Right.
then make these two talks, and you can send the announcement maybe
Okay.
now so people know what will happen.
Okay.
Yeah. And Andrei, will you can say announce talk on this information theory seminar probably?
No, it's Marius who can announce it. Okay, or I can
Marius is here
share.
still.
I can show you the official announcement.
Yeah, so this Wednesday I'll talk about a result of Ilango, Ren, and Santanam showing a characterization of one-wave functions in terms of Kolmogorov complexity.
Yeah. And maybe if it will be too short, maybe you can explain for more stupid people here at some point again. I guess it's not easy to understand, so it won't hurt if you being slow.
Yes, so you mean to do the
Wait, I see terrible error. It's I should fix it immediately. It's not 11 hours of Paris time. It's 17 hours.
17.
Right? It's 5 p.m. Why did
I hope so,
Usually
yeah.
we have 5 p.m. Yeah, but
Yeah. Okay. I will fix it immediately. I hope I haven't wrote the same stupid thing in the email.
I think for Marius it would be quite
Yeah,
strange
it would
to
be a
give
problem.
talk.
Yeah. I don't know. No, it's
Okay, then we.
No, but I don't know. I saw 17.
Yeah.
Yeah,
Now
17,
we
yeah.
immediately
It was
change the
17,
date and
yeah.
send the announcement with correction.
Yeah.
Yeah. Okay.
Yeah, so that's
Okay,
5.
but I
5
strongly
p.m.
recommend it's
5 p.m. Yeah.
strongly recommend to come to this seminar so we can be more prepared to the if there'll be a slow continuation. So please have this in mind. Okay.
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 Thank you.
Bye, everyone.